I'm really glad that I get to speak after Stephen there in his super slick, snazzy, rolly presentation. Because what I'm going to be talking about here is the kind of the other side of this, the flip side of what went into building that stuff. My code is the best code in the world. It's really very, very good. My classes are the best classes. I got the best classes. My classes all have methods. Or variables. The best variables. Believe me, these things are the best classes. And that is the truth. People of audio, together, we can make coding great again. I propose to build a great firewall around C++, and I will make PHP pay for it. Apologies to all the Trump supporters in the room. I couldn't resist a little last minute joke about the guy. If you're watching this talk on video in the future, of course, maybe he won, and maybe I was put up against the Mexican wall and shot with all the other anti-Trump sympathizers. But I'm English, and we don't approve of this kind of showing off, locker room banter, macho nonsense. But I have to admit, and I know I'm not alone in this, that I do occasionally have a bit of a secret inner Trump moment. A bit of an ego moment where I've spent a bit too long polishing some code, and I think to myself, yeah, that is the best class. You know, nobody could have written a better class than that. It is the best class in the world. And I know that's never true. And I know you always go back to it a year later and think, what idiot wrote this? But it's that kind of feeling of satisfaction that makes this job worthwhile. And I think it's a really positive thing to be proud of some work you've done in private. Of course, nobody should ever stand up in public like Trump and brag about how great their achievements are. So my talk today is mainly about how great I've been recently in solving some of the problems that we had getting this thing out the door. For this conference last year, my keynote was mainly about a kind of silly programming stunt that I did where I rewrote zlib. And I did that for the purposes of that talk, just to make a point about how you should always try and make your code better and not be satisfied. So this year, it's sort of a tradition I'm going to continue where I talk about a silly programming stunt that I've done. But this year, it's one that I did actually in real life because we needed to do it to make this thing work. There's a famous scene in the movie Jaws where the divers are sitting around drinking and showing off their scars and seeing who's been bitten by the biggest, nastiest sea creature. And hopefully this will be a bit like that, showing my programming scars over the last few months. It certainly felt like during this project we kind of needed a bigger boat sometimes. So last year's theme was to encourage you guys to not be satisfied just with code that works, but to really take pride in making your code elegant as well as just functional. If there's some kind of theme this year, I guess it's to encourage you to be, it's for me to set a bad example and encourage you to be a bit more badass and a bit more adventurous and maybe try and do things in a bit more of a showy off kind of way. You know, to attempt that double twisting backflip somersault. And you know, 9 times out of 10 you will land on your head, but there's no pain, no gain. So in the story that I'll be telling here, we were kind of in an unusual position where the only way to get out of a burning building's window was to do a double twisting backflip somersault. So that's a bit unusual, but you can do somersaults for fun too. Of course, if you try a fancy coding maneuver at work and screw up and your boss fires you, then sorry. So this isn't, like last year, this isn't good career advice. It's just locker room banter. So hands up who's created their own language. Whoa, quite a few. That must be 10. Good work. Good crowd we've got. So who of you guys have created a language that's used by anyone other than you? Still a few hands? Good. So who's written the compiler? Hopefully as many hands or more. Yeah, more. Ooh, that's pretty good. That's like 10% of the room has written the compiler. Good job. Who's coded some sort of bytecode interpreter? Yeah, we have a stellar crowd here today. Well, these are all really great bucket list items if you're a really serious hardcore programmer. And working as a library author for most of my career, I've done loads of bucket list items. You get to do those in libraries. But I'd never really done the whole compiler thing. That's mainly because of this. Like the world really doesn't need another language, or even a compiler these days. But it's a fascinating thing to do, and it's the kind of thing that a lot of coders will do as a tinkering around hobby project, or maybe you did one at a university course. You know, they said write a toy language or a toy bytecode, and it's a really, really interesting thing to do. But the reasons you do it are generally not business reasons. I did write a JavaScript interpreter a few years ago for JUCE, but it's not really a compiler. I mean, that thing, it parses JavaScript, it creates a graph of C++ objects, and then it runs those objects with just by calling virtual functions on them. So it kind of does the parsing stuff, but it's not generating assembly language or bytecode or anything like a real compiler does. And as for designing the next great language that's going to take over the world, well, you know, like most of us, I've kind of pondered ideas of greatness. But honestly, you know, does the world need yet another language that's an improvement on C++? And even if you think you've got a really killer idea for that kind of thing, these guys are doing a really great job of nailing that space. I mean, even if you're just thinking of systems languages, we've already got like here's 6 really good ones, and that's just a small subset of new languages. So designing a language is an intellectual exercise, great, interesting, fun, you learn a lot, but to expect anyone to actually adopt it in real life is kind of optimistic unless you happen to be Google or Apple or Mozilla. And people do write domain-specific languages, little tiny languages in the course of doing big projects, but they don't tend to be, they tend to do one small thing. Maybe it's a format for a script file or something. But what I'm talking about here is actually a real general-purpose C-like language. So I want to spend most of this talk talking about constraints. When you're writing code, you generally work under some constraints. If you're lucky, very few. If you're unlucky, lots. Depending on the type of work you're doing, you're going to hit different constraints from this random order, random list of ideas here. So if you're a web coder, you're not too worried about CPU speed or memory. You can buy more of that. But you are worried about bandwidth and deadlines. But you're also not going to worry about code dependencies. If you're writing a web server, these guys just fill the web servers with every third-party library they can find to do every little bit of utility code. They don't worry about deployment. If you're writing some sort of number crunching, big data supercomputer, you're all about the CPU speed and bandwidth and memory. If you're writing the control system for an airliner, reliability is the only thing that matters. For me, writing things like JUCE, code dependencies are really important. We don't want to burden our users with having to install a load of dependencies just to use our library code. If you're doing a desktop app, CPU, yeah, that's fine. They're pretty fast these days. Mobile app, less so, depends what you're doing. But normally, most projects are going to have a few tough constraints, and most of it you can kind of relax. Well, we just launched this lovely new Lightpad. You saw the slick videos just now. It's a box with silicon on the front. This is my less on-brand product pitch. It's got silicon on top, some LEDs in it, pressure sensors, these fancy new magnetic connectors. It's actually pretty cool. And a few months ago, I got dragged into this project because we want to provide an SDK for this thing. We want people to use it for things that are non-musical. And I'm the library guy, so they said, hey, Jules, write us an SDK. So, you know, you think of this thing as, picture it as a little, very, very low-res touchscreen with a little CPU in it. What can we do with this? It's pretty straightforward. It's got 15 by 15 LEDs. Now, if you get out your mobile phone and you try and a magnifying glass and you try and zoom in on 15 by 15 pixels, it's really small. It's like maybe a millimeter in size. And these mobile phones nowadays, they can effortlessly animate the whole screen, millions and millions of pixels flying around. So animations on here, it's not going to be a problem, right? Even with a little embedded CPU. It already had, when I came to the project, it already had firmware that was detecting all the touches, doing all the finger tracking, all done, same as on the C board, no problem. So a couple of weeks for me to throw together an SDK that lets you draw on the screen, pick up the touches. Hey, yeah, easy, right? Okay, so let's go back to that list of constraints. And let's see how this stacks up on these constraints. CPU, actually not too bad. Obviously on the host computer that's talking to the SDK, We don't care. You've got loads of CPU. On the device itself, it's actually still not too bad. We've got actually 2 embedded chips in this guy, and they have a fairly respectable speed of over 200 megahertz. You can actually do quite a lot, and they're not even very busy. They're doing like housekeeping tasks of controlling the LEDs, picking up the finger movements, that kind of stuff. But there's some spare clock cycles in there we can use. Bandwidth. Now, at first, I didn't give this much thought. You don't, do you? I mean, nowadays, you happily stream a high-def video. You just take this stuff for granted. And USB, we're going to plug this in over USB. USB is really fast. There's a thing called DisplayPort, which is a protocol for driving a whole full proper monitor over USB. So 15 by 15 pixels over USB, that's going to be a no-brainer, right? This is easy. Even with a really naive compression algorithm that I hacked together in an afternoon, and I did hack it together in an afternoon. The protocol that they talk over USB or Bluetooth is actually MIDI, and there are good reasons for that choice. Mainly that it makes it very easy to connect the blocks to a MIDI device or mobile devices without any security hassles. But even if we decided that MIDI was a bad idea in this case, it was too late at this point to change that. So the whole stick a Wi-Fi chip in it idea, that's not really an option. But that's fine. You know, I could do a whole talk on why MIDI is bad. I think if you go to Ben Supper's talk tomorrow, he probably isn't going to say all complimentary things about MIDI and MPE. But you know, it's a known quantity. We've got sysexes. We can send arbitrary data backwards and forwards. There's a bit of overhead with packet headers and 7 bits and blah, blah, blah. It's annoying, but we can abstract that, and we can get data in and out of this thing over MIDI. That's fine. So, easy stuff. Did that, hacked together some code. I sketched out a nice simple API where you could use a JUCE graphics context to draw onto the screen. And the changes you made to the pixels got whooshed across to the device and appears on screen. At this point, I had like an experimental early prototype board connected by USB. It'll work just fine. Well, actually, I had about 2 weeks of pain getting it working because MIDI happily drops packets. So error correction was just a total nightmare to get working here. But basically, it was pretty straightforward. We got it working. We had lovely animations of random things happening. There have been a few mutterings in the team going, oh, you know, it's got to work on Bluetooth as well. Is that going to be all right? Bandwidth's a bit lower. And I'm like, okay. But I've always been one to say, never prematurely optimize. You know, it works. We'll get it going. When we have a Bluetooth system, we'll test it. And then, if we need to, we'll optimize. So we did things the straightforward way, got a Bluetooth unit, and it was appalling. The speeds you get on MIDI over Bluetooth are just dreadful, maybe a few hundred bytes a second if you're lucky. I don't know what speed this modem in this picture is, but it's probably in the same kind of ballpark. It's not just slow, it also drops packets like a baby drops toys. The code that I wrote that was happily animating 25 hertz animations on the USB was just no way. It was like maybe 1 frame per second. This is not the responsive, lovely experience that you saw in those glitzy videos just now. And it gets worse because, like you saw, the whole point of blocks is it's a modular system. You just snap these things together and they talk across their DNA connectors and exchange information. And this makes the problem much harder in some interesting ways. It means that if you have a whole set of blocks, they have one connection. So not only do you have to worry about bandwidth to drive one block, but you might have to do multiple blocks. And they also have to talk to each other. And these DNA connectors are they're magnetically held together. They're not a proper plugged-in connection, and they're not super fast because it's all very tenuous electronically. So we've got this mesh network now with messages flying backwards and forwards, and this gets very hairy. Now, the app works at the moment with 4 blocks, but Roland, our CEO, keeps coming up and saying things like, hey, Jules, maybe we could build a whole wall of blocks. Do you think you could just try that? And you know, you can hold them off for so long, but we certainly want these things to work in big, you know, maybe 10 or more setups so that we can do crazy controller systems for big, ambitious projects. So this is going to have to work. So, okay, what do we do? Surely this is just a case of doing better graphics compression. I mean, this thing's just a video is being played on some LEDs, right? Easy. I mean, really, really smart people have spent decades refining incredible graphics compression techniques. And we can play high-def movies with ludicrous compression ratios. They look great. We can just still use some of those techniques, right? We can just compress this stuff better. And yeah, modern graphics compression is really, really smart. But it's designed for huge images. And they generally rely on a process of breaking the image down into small blocks and compressing those blocks and watching where those blocks move around. And one block in a typical MPEG compression algorithm is probably not much different to the size of our entire display. These things just don't scale down. And also they rely on sending a sequence of changes. And we need this to be really responsive. We can't just buffer up multiple frames. We need it to happen like right away so that we have really low latency responses on these guys. So let's face it, we can't send graphics to these. You just can't do it. Not even at 15 by 15. But our minimum spec is for flashing jump pads, finger trails, colored layouts that pulse and bounce around, and the whole thing needs to fade in and out. We want a step sequence view with little rotating dials. To achieve at least that, given so little bandwidth, the only real way to do this realistically is not to send graphic, but to send semantic data. So we send it like a byte that says, hey, flash this pad now. A couple of bytes that say, draw a finger trail moving over here. Another byte that says, the pads are now in 4x4 mode. So you have to really break it down to the data that's semantically relevant for the task you're doing. And the obvious implementation for doing that is really simple. You just list all the things we want the pads to do, then we hard code that into the firmware. When we send these messages, we have a list of messages like flash pad. And you know, that's great, but it makes the blocks a single purpose device. And that made me really unhappy because I really want people to be able to hack these things and use them as open general purpose controllers. You know, maybe someone wants to turn one into a wacky DJ controller or a DAW controller or a 3D CAD controller. And you know, maybe they just want to play Pong on it. But hey, this is not so bad. Just because all the animation has to happen in the device doesn't mean we have to hard code all that into the firmware. We can just run a script language, right? Give it a script, the app can send the script, the device can run the script, and it can do whatever kind of crazy animation it needs. The script and the app can know what kind of semantic data to send across. Boom, done. We can do all of our own really jump pad designs in this way. Other people can do their own designs in this way. Everybody's happy. So, okay, good. Right, job done. We'll just make this thing run JavaScript or Lua or some kind of simple scripting language. It doesn't need to be super fast because, like I say, CPU is all right, you know. To draw a few, turn on a few LEDs, you know, a scripting language can do that quite easily. Okay, next constraint, memory. Yeah, this is a screenshot of the last time I did any programming to the kind of memory constraints that we're under for this scripting language. These words are burned into my memory. It's from about 1981. This is a VIC-20, and 3583 bytes to be ready into my child's brain. I'll never forget that. And at that time in 1981 or 2, it seemed like a miracle that a machine could remember 3,583 things. The pad block has more than this. A gargantuan 64K. I literally fantasized about 64K back in 1982. But that 64K includes all the code that's running on the device, which includes like all the stuff to drive the LEDs and to do the touch detection and all the housekeeping, the comms, and most of that was already spoken for. Like the firmware guys, they said to me, well, you know, we could spare 4K. Maybe 8K if we kind of clean up a few other things and squash a few things around. Oh, but that has to include both the code to run the script and all the memory that the script uses when it's running. Okay. So, right, that's fine. we'll find just a really small scripting language. I mean, these things exist, like Lua. Everyone talks about Lua as being really, really small. Well, it is small, it's tiny by desktop standards, but it's not even close to this scale. What about my lovely JUCE JavaScript interpreter? I was really proud of that because I managed to fit it into 2,000 lines of code, and I was like, yes, this is the smallest JavaScript parser in the world. And it probably is, but it's 2,000 lines of code, even if that's 1 byte per line when you compile it, not even counting all the dependencies and strings and arrays and things it uses, nah, ain't gonna work. And in fact, with any kind of script language, you've got a problem, because if you've only got 4K, if you pass a script which is 2K, you've got to parse that. You've already got no space to parse it. Things like my JavaScript parser uses C++ objects. Lua uses a kind of bytecode. They have to generate that from the script and then run the bytecode, and we've got no space for that. Well, what else can we do? Well, Forth is supposed to be pretty small, right? This was the 1980s most famous Forth machine. And yeah, I did find a Forth implementation called MicroForth or something, which probably would have just about squeezed into here, but let's face it, Forth is pretty awful. And we do want people to use this. I'll also offend a few people by saying I'm not really a fan of Lisp either. Lisp feels to me like Forth, but not quite so ugly. Lisp also would not quite fit it in because that kind of uses a heap and it's all about lists which have to be allocated, and some Lisps even need a garbage collector. I did find like a micro Lisp which may, if we poked it around, just about fitted in. I mean, I guess we could have used Vic20 Basic, but that's even worse than Lisp. Okay, so what is the most efficient compact format which we could possibly send a small program onto a device for it to run? This has to be something we don't need to parse because we can't do that. And this thing can't expect to be allocating a heap or objects or arrays or any of that high-level language stuff. Well, the absolutely optimum solution here is surely to send it some ARM assembly code. This is I seem to be on a bit of an 80s theme with my pictures. This is the first, this is Archimedes RISC machine, the Acorn Archimedes, the first ARM-based CPU. The pad block has a slightly newer ARM chip than this, with slightly more memory, maybe. But the ARM chip is great because it was designed by very smart people to have a tiny instruction set. It really is the best possible thing we could send to this block for it to run both fast, small, compact, no overhead. Next constraint. Okay, security. Yeah. Sending raw machine code for a bare metal CPU to run with no memory protection or operating system doesn't really pass the security test. We're not really worried about this guy. We don't care about the hackers. If people want to take these blocks and hack them, replace the firmware, great, go for it. As long as you understand that it voids your warranty. Unfortunately, the big issue for us is not really people hacking it, it's people bricking it. So if we had a way where you could give some raw assembly language to this thing, and then it writes over the flash, and you can't get this thing running again, you'd have to package it up, send it to our factory in Mexico, where someone would unpack it, dismantle it with a special screwdriver, drill a hole through some plastic to get to the circuit board, attach a thing that does something to the flash memory, put it all back together, fix the plastic, package it up, post it back to you. Very expensive. Our support team would really not be happy if I provided a way for people to just start randomly bricking them. And there's another aspect to the system where raw machine code becomes a bit annoying as well. This is a bare metal machine. It has no operating system. There's no multitasking. It's single-threaded. It has interrupts. But if the program that someone sends to it was to take too long to run, then other stuff wouldn't happen. We wouldn't get our lovely touch events being processed and the LEDs being driven. So we kind of need a way to control the execution and interrupt the program that someone wants to run on here. So really, the easiest solution here is to have some sort of interpreter so that we can both control what the program does and when it does it, and we can start and stop it. And what I actually ended up implementing was the world's dumbest scheduler, where every millisecond I run a bit of interpreted code for half a millisecond. It does the job for now. Next constraint. This is a lovely graph of package dependencies in Linux. I don't know what the center is. At this point, we've decided to use some sort of bytecode, whether I write that or it pre-exists, whatever, and an interpreter. I did end up writing the bytecode because we couldn't find one that did the job. But then what language are we going to use in the API to write this bytecode in? I think the OpenGL shader guys got it right when they did OpenGL shaders with a very simple C-like cut-down C language. That's nice, we can all understand it, does the job nicely. So I needed a compiler that would turn something like that into my own bytecode. Now, I've always hated dependencies in my code. In JUCE, we have a golden rule that you just don't bring in third-party dependencies. That's a self-imposed constraint, but it does make things a lot easier for our users. And for the blocks SDK, same thing applies. We don't want to pull in third-party stuff for this. So we're not going to put Clang or LLVM in there because it's like the biggest dependency you could possibly find. We're also not going to put Boost in there and some of its great parser tools because that's also a bit of a black hole in terms of code compile time and dependencies. So what other compilers were there? Well, I found a couple of minimal C compilers out there. There was a thing called TinyC, I think. But it seemed that figuring out how this compiler works and then replacing its entire Intel instruction set with my own instruction set was kind of more of a pain in the neck than just writing a compiler. So I went for that option. Next constraint, reliability. All code obviously should be reliable, but let's think about what the challenges were on this project. So we've got an app on a phone or computer, and it's talking via a flaky MIDI connection to a device which is then connected by easily breakable magnetic connectors to multiple other devices. It's spewing messages left, right, and center, and they're being lost. All those errors need to be recovered. So actually implementing the interpreter on this thing is actually an easier problem than just getting the bytecode that you want to run onto the device intact. So, and to keep things as simple as possible, what I ended up doing was to use a single error checking system to both get the program onto the machine and also to control the program while it's running. So what we ended up with here is, on the device itself, here's our 4K that we're going to use. The first 2/3 of it we're going to use for the program itself, the bytecode, and some heap memory. It's not really a heap, but I'll call it a heap. A stack we put at the end. And then on the host computer or phone, we have a mirror of this. And then we have in between a big complicated system of error correction that makes sure whatever you want to set in the bytes on the right-hand side gets flushed across to the left-hand side and onto the device. So the compiler just has to compile, puts its bytecode into the program area, things magically get flushed across, the program appears here, the device runs it, and then in the heap area, the running program can then twiddle bytes in this heap to say things like, this byte controls the pad size, or this byte is the position of a finger trail, or this byte is the color of a pad. And then just the change bytes get flushed across. Last constraint. Not much to say about this, except that in my entire career, I've never been up against such a ridiculous deadline as this one. And the time that didn't make a bit of a difference to the language, in that I didn't quite get time to add a few niceties like arrays, which would make things easier, and optimization, more optimization. But we can add that sort of thing later. So, the language I wrote, I ended up calling Littlefoot, because its whole point, the reason it exists is it's got a very small footprint. Like Bigfoot, it has very little impact on its immediate ecosystem. It's rarely spotted in the wild. It's a little indistinct in snapshots because we didn't have a lot of time to really do good documentation about the syntax. But we've published all the code for this. It's all there. It was released yesterday. It's in JUCE. Just pull JUCE and you've got this stuff. And once I get a chance, I'd like to go back and add some more extensive comments to it to really help people see what's going on in the compiler and the interpreter. Because one of the interesting things about working with such a tiny, tiny space to work in is that the code I ended up with is a really good example of how to write a simple compiler. And I hope it actually works out to be useful educationally for people to learn how you do this in a really simple way. Because if you start looking at LLVM or GCC, you're not going to get very far. The Littlefoot language itself doesn't really need much explanation. I think you'll get the gist of it. This does that. It draws a moving rectangle. We have a repaint function which the device is going to call 25 times a second, and it calls, hey, fill rect. Here's a real program that we use in the real world, and this one just makes the pad display an arbitrary RGB bitmap. So all this does is it uses a bit of that heap memory as an RGB table, and every time we repaint, we just look up the color from this get heap bits function, set the LED, and that's what we use in, like David Zuccarelli is going to be showing some Max examples, and this is kind of what he's using. So he's working with with bitmaps rather than low-level programs. You could use variations on this. If you're like me, you're an 80s throwback, you might want to do a palletized version, so you can have instead of just RGBs, you could have a palette and some palette indexes and do kind of 80s retro style palette animations. The syntax is just C with things removed. So we don't have pointers, we don't have arrays, we don't have structures, just a few functions and 32-bit ints, floats, and bools. This is a bird's eye view of the program that we use in Noise to draw all of the drum pad controls. So if you want to look at it in detail, it's in the SDK, you can go and have a look yourself. This is the 1,000-foot view. This compiles down to about 2K of bytecode, and it's what's doing that stuff that you can see there on the right. Back over in C++ land, this is the interpreter. Last year in my talk I did this 10,000-foot bird's eye view, and people seem to like it. I think it's nice to get a high-level view of the overall structure of some code. The interpreter's header only, one file. It's about 800 lines. I was annoyed it was so big, couldn't quite get it any smaller. And because it's running on this tiny bare metal platform, it's dependency free, and I mean like 0 dependencies. This thing doesn't have the C library or the standard library. There are no includes. Zooming in a little bit, these are the opcodes that I decided to use. To be honest, I did 0 research into existing instruction sets before I started on this. I kind of have the gist of how they work, so I just went for it. It's a stack machine, so it's all about pushing and popping. You've got some instructions to do things like push onto the stack, pop things out of the stack. Very importantly, there are things to pop out of the stack from positions other than the top of the stack, because that's how local variables work. And as a side note on that, local variables were probably the hard bit to get working. So if you ever do a compiler, good luck with the local variables. The theory behind them is really simple. They live on the stack. You address them relative not to an absolute address, but to the stack pointer. But actually working out where they are relative to the stack pointer at all points in your code is the hard bit. I've never really understood why real assembly language has such tiny little names. So mine have all got long names. And I love this XMacro technique. I think if I was only going to use macros for one thing, and hopefully I will only ever use them for one thing, this would be it. It's really handy. This macro here declares all the operators, and then we can reuse it in different places. Like, so here we use it to turn that into an enum of those operators, and then later on we have the main interpreter switch statement, which actually looks at the incoming bytes in the bytecode and jumps to do the right thing. And it would call similarly named functions like this. So it's all quite neat. Please do go in and dig around in there, and I'd be happy to talk more about that if anyone's interested. This is the bird's eye view of the compiler, which is a bit bigger, 2,000 lines. Again, one file, header only. I should probably split that up a bit, but most of what you have in the compiler are little classes for different types of syntax object. And this guy does get to depend on JUCE, so we have a few useful functions to rely on, which makes the job a little bit easier. I'm not going to spend any time going into depth about it. You can dig around if you're interested, but really quick whiz through. XMacro again with our keywords and operators. Then we have a TokenIterator that iterates your script. That feeds into a syntax tree builder, which is a good old-fashioned recursive descent parser, like you see in the textbooks. I pinched a lot of this code from my JavaScript interpreter, which is kind of similar. That stuff spits out a bunch of these statement and expression objects. And one lovely optimization here that I stole from LLVM that you can do when building syntax trees is that when you're compiling a program, you end up with a big old graph of these things. You've got statements with substatements and expressions with sub-expressions, pointers going all over the place. And if you try to manage this with proper C++ memory management techniques like unique pitters and reference counting, it gets really hard and messy. So what you do is you just have one big pool. As you're compiling, every one of these you allocate, you put in the pool, and then you just use these raw pointers everywhere. So we have statement pitter, expitter, you don't care, raw pointers. And then when the compilation is done, boom, throw it all away. And it's one of those lovely, satisfying optimizations where it makes the code simpler and faster and safer. So once you've got your big tree of statements, we do the next step, which is to convert that to bytecode. This is a really quick example. This is the if statement. Just goes boom, 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 emits some opcodes. Doesn't matter, you can look in detail. And then quick pass of optimization, a bit of address resolution, bung it into one of these program objects, and this is what the interpreter actually runs. So it was a really, really fascinating process to write this. I mean, having used compilers for so many years, and I had pretty good understanding of how they work, but it's always different to actually do this yourself and see it from the other side. Some stuff was surprisingly tricky, like using local variables and stack unwinding. But some other things were easier than you'd expect, like actually parsing the syntax was actually pretty simple. Although it seemed to me, when I started this, that doing the language, I took myself into doing the language, and it seemed like the only sensible way of actually getting this stuff out the door. I still had to convince a few people I wasn't mad. And that this was something that we could feasibly put into production within a couple of months. And in fact, as is often the case in this kind of situation, the best way to do it is to go a bit skunkworks. Luckily, I was on paternity leave in July, and in between changing diapers and screaming fits at 3 a.m., to keep my brain alive, I sat and I tinkered around and I got this language working, and I had a little bit of a proof of concept to come back to work with. So I said, actually, look, it does work. We can do this. We can make this thing work. I've no idea if anyone's going to be using this language in 10 years' time or 10 weeks' time. It doesn't really matter. Things will move faster. I mean, maybe the next iteration of the blocks platform will have proper big processors in there with loads of memory, and we just forget all this and write this all in some woolly language like Python. But it's been really interesting to do, and it did get us out the door. So this wasn't just a personal learning experience for me, but it was actually a good business decision. And a footnote about being a badass developer, because that's kind of my theme today, is like, I want to encourage you to be a bit more gung-ho in your approach to some problems. Final rant about this, reflection on the blocks project, is that all I contributed to it was the language, a compiler, an interpreter, an SDK, a topology system, and some architectural guidance. And normally that's a pretty impressive, badass bit of work. But the overall badassery level in the team as a whole in getting this thing out the door actually made what I did seem pretty average. Like, we don't just plug these blocks together with off-the-shelf USB cables or something. We designed and patented our own physical ports and our own interconnect protocol. We wrote the mesh networking system that they talk. It has a custom radio comm system as well to complement the physical interconnects. I mean, I don't even understand what's so clever about the electronics. I don't really do electronics, but apparently there's some pretty good stuff going on in there. The silicon design took this incredible level of material design artistry to get a balance between playability, durability, feel, the cost, manufacturing, and all these other factors that I don't even know about. And that's just the hardware. Like, once the data from this machine finally reaches the host computer through all the error checking stuff that I wrote, it ends up in a noise app, and then that's a whole universe of badassery. Like the whole software stack in there is written in JUCE, so that's all in-house. But the GUI is built with like a whole new layout system that was written especially for this, which Vlad will be talking about tomorrow. The visualizations are all custom OpenGL fanciness. The amazing jump sounds that really bring it to life are a whole new synth engine that the FXpansion guys designed from scratch. We embedded an improved version of the Rowley Equator engine in there for the melodic synths. The sequencing is all done by making an embedded version of the traction door engine and getting it to run on an iPad inside this thing, and then rewriting it so that it can do loops as well as just normal playback. And then we threw in a social network online as well for this thing. When you get a critical mass of people involved in a project where everyone's really excited about doing work that's really goes beyond the ordinary, it becomes this kind of infectious. It's infectious. You get some real innovation happening, and it becomes really exciting to work on that. So we managed to achieve that in this project, and I hope you guys, in the stuff that you do, also manage to find a way to get that same magic in some projects. And I hope you get a longer deadline. So apologies that whenever I do a keynote at a JUCE or audio conference, I never really tend to talk about JUCE or audio. I kind of always prefer to use the opportunity to push the message of become a better programmer rather than digging into technical detail. But we have oodles of technical meaty goodness over the next 2 days for you guys. All aspects of audio, C++, JUCE, and other super geeky subjects are going to be covered. I'm going to have dilemmas at every point in the conference about which talk to go to, and that's a sign of some great content. So I hope you all have a wonderful time, and I hope you all go away just a little bit smarter than you arrived. Thank you very much.